All right, so now we're going to talk about matrix reduction. And this has to do with, again, the question of how do you go about computing homology. And the essence, if you will, is that the boundary operator, of course, which is the fundamental object which induces homology, can be expressed in terms of a matrix. There's a way to reduce that matrix into a particular normal form, which then reveals, if you will, it's like the homology of the superficial complex. Okay, so the homology groups of a triangulated space can be computed from the matrices which represent the boundary operator. And of course, it should be fairly obvious that you can do this. It's like in terms of matrices, because if you think about it, the chain groups of, say, a superficial complex are all finitely generated. So you're, in some sense, in some sort of finite dimensional vector space. Okay, and the boundary operator is also a linear transformation. So, so you also have a situation where you can represent it as a matrix. Okay. So, so the reduced versions, if you will, of this matrix, then this matrix provides, well, actually matrices, because there's a matrix for each of the boundary operators, right? The ranks the cycle and boundary groups. And then the difference of these ranks give you the Betty numbers, which are associated with the rank of the homology groups. So before we do that, it's like what we're going to do is that we're going to go back and talk a little bit about the Euler characteristic, which if you recall, it's like we discussed in the context of triangulated two manifolds, right? So it has to do with the alternating sum of the number of, it's like vertices, edges, it's like in triangles, if you will, in a triangulated two surface, okay? And there's a generalization, if you will, it's like of that formula called the Olipocry Formula. Okay, as it turns out, you can relate it to the Betty numbers. Okay, so previously we had expressed it in terms of essentially the rank, if you will, it's like of the chain group, and we're going to show that because of the relationships between the ranks of the chain groups and the Betty numbers, okay, in some sort of indirect way, you can express the Euler characteristic, it's like in terms of an alternating sum of the Betty numbers instead. Okay, so this is the Olipocry formula. Okay, so again, as I mentioned before, the Euler characteristic is the alternating sum of the number of simplices in each dimension. course, this is nothing more than the rank of the relevant chain group, right? So the rank of CP, if you will. Okay. So I'm going to write down, it's like a few letters, it's like corresponding to ranks of the cycle groups and the boundary groups, right? So I'm going to call little zp the rank of the p cycle group, right? Vp is the rank of the p boundary group. Okay, and then you know, of course, that the Betti number beta p is the difference, right? Zp minus bp. And then I'm going to call this rank of CP what I call NP. NP is the rank of CP. Okay. So again, these are the cycles, the boundaries, right? These are the homologies. And then this is the chains, if you will. Right, so there's a sum of the fundamental objects. It's like, and they're obviously related in some way. All right, so far it's like we're a relationship between ZP, BP, it's like a beta P, but we don't yet have a relationship, it's like which involves the rank of the chain group. Okay, so where we can see this is that you might have heard of the rank and nullity theorem. Okay, which more or less says that you know. And I guess I should also say that the rank and nullity is like going to be related to the sort of the dimension of the cycle groups. It's like in the boundary groups, okay? Because of course it's like the boundaries that's like are in the kernel of the operator, if you will, for example, right? So so the observation, if you will, is that by the rank and nullity theorem, sort of applied to the boundary operator, which is a linear operator, right? We have that the rank of the chains NP is equal to ZP plus VP minus 1. Okay, so right. So I should, yeah. So because of course the cycles are the ones that which map to 0, so they're in the nullity, if you will, right? And then it's like BP is the image of the boundary map, which is related to the rank, right? Okay, so you have this kind of relationship, okay? So so we know that the Euler characteristic, right? Euler characteristic is the alternating sum of the number of simplices in each dimension, right? This is really nothing more than what I'm calling NP, which is the rank of the chain group. Okay, so the Euler characteristic is equal to the sum from p greater than or equal to 0 of minus 1 to p, right, NP. Okay, that's sort of just a definition. Then we first use this relationship that NP is ZP plus BP minus 1. This is equal to the sum from p greater than or equal to 0 of minus 1 to p of ZP plus BP minus 1. Okay, and then what I'm going to do is that I'm going to reindex the sum. It's like involving the Vp minus 1s. Okay, so right. So this is going to be the sum from p greater than or equal to 0 of minus 1 to the p of zp minus vp. Okay, and then the minus sign here comes from the fact that if you take this, it's I can give and rewrite the sum in terms of, say, L is equal to p minus 1, right? And then it's like replace L back with p again. It's like you get an additional power of minus 1. It's like which I'm going to put here. Okay, so this is really just sort of a relatively standard reindexing trick. Okay, and then so I'm just going to try to leave it's like what we had here, right at the bottom, right? So, but of course, Zp minus Vp is exactly the Betti numbers, right? So this is equal to the sum from p greater than or equal to 0 of minus 1 to the p beta p. Okay, so that's quite nice, right? So now it's like what this is telling you is that you have an alternating sum. It's like involving the number of simplices, and now I've replaced it. It's like to something which involves the alternating sum of the Betti numbers. So why is this significant? Well, this is significant, obviously, for a variety of reasons. One of which is the following, right? If you have an alternating sum of the rank of the chain groups, right, then this expression, at least on the surface, doesn't look as if it is independent of the choice of triangulation, right? So, for example, if you have a triangulation that's like of a space, and then you do barycentric subdivision, then clearly it's like all the number of simplices that's like what you have in each dimension is going to change, right? So these NPs are all going to change, and so it's not at all clear that the Euler characteristic, as it's written here in terms of the alternating sum of the rank of the chain groups, right, would be independent of the choice of triangulation. Whereas here, if you wrote it, it's like as an alternating sum of the Betti numbers, then you would be in a situation, it's like where you would still have to show that, certain things, leave the Betti numbers invariant, but then it's sort of clear that, the Euler characteristic is, in some sense, as invariant, if you will, as the homology, it's like of the space. Okay, so the advantage, if you will, of this expression then is that it's clear that all characteristic can be derived. It's like from things which just have to do with homology. Okay. So let me sort of just say that a little bit, right? So the original expression is not obviously sort of independent, if you will, of the discretization. So let me rephrase that, the triangulation, if you will, of the space. And again, as I sort of mentioned, if you did something like barycentric subdivision, it's like of a triangulated space, and obviously all the number of simplices in each dimension is going to change. Okay, but the alternating sum of the Betti numbers, right, clearly only depends on homology. Okay, so one would still have to show that the homology is independent of the choice of triangulation, which of course takes a little bit of effort. And there are many ways to sort of think about this. One way has to do with introducing sort of more general notions of homology. So far we've been essentially working in what is called simplicial homology. There are generalizations like singular homology, where it's a little bit clearer. It's like how this notion of homology is independent of the choice of triangulation. Okay, so I should just remark that still need to show that homology is independent of triangulation, right? And that's really beyond the scope of this class, but I'm certainly happy to refer you to references if you're interested in sort of seeing where that's true. All right. Okay. So, yes, so the other remark is that it's not just that it's independent of triangulation, right, but that if you have things which are homotopy equivalent, they also have the same homology, right? So the other remark is that homotopy equivalent spaces have isomorphic homology groups. Okay, so again, it's like I'm not really going to show that. So anyway, so the calculation, which unfortunately I just erased, right, then sort of gives you what is called the Olipocry theorem. In the sense that the Euler characteristic of the topological space is the alternating sum of its Betti numbers equal to the sum from p greater than or equal to 0 of minus 1 to the p greater than p. Okay. All right. So let me just stop here for now. It's like, and then in a little bit we'll talk about how to represent boundary operators. It's like in terms of boundary matrices, and then what you can do with them. Okay. So let's stop for now.